And as you can see, the prognoses were inserted prior to the fault detection tests in our flow diagram. And if we click on the last node in the diagram, we can see that we're now detecting 70% of our expected failures, even though only 60% of our functions are diagnosed in full. And if we run the detection order report, the first thing that we see is that the 3 prognoses are listed using a different color in a single statement at the beginning of the detection order table. Generally speaking, when tests in a calculated sequence are listed in Express, the color magenta will be used for prognostic measurements and the color blue will be used for diagnostic tests. Also, we can see here that the detection test for box B was removed from the detection sequence. This is because, based on our settings, all failures to box B can be prognosed with 100% confidence, meaning that they will never occur and therefore never need to be diagnosed. Now, in this report, we can see that 40% of our failures are indeed prognosed. And also, for the first detection test, the probability detected has been reduced by the amount prognosed. In the summary block, the aggregate failure rate is still 500 since we're still basing our analysis on the full set of possible failures. And the probability weighted detection percentage is 70%, the same number as the final cumulative value in the probability detected column. Now, if the analyst wishes to list the 3 prognoses as separate entries in the detection order table, this can be done using a setting on the Report Options dialog. On this dialog, there's a checkbox that's used to specify whether or not prognoses should be combined into a single entry in the table. This entry is selected by default. Let's run the report with this option disabled. And in the detection order table, we find that separate entries are now included for each individual prognosis. So, when a prognostic sequence has been generated within a diagnostic study, then all diagnostic analyses within Express include prognosed failures in their calculations. This can be seen not only in the detection order report, but also in any of the other reports or panels with numbers that are based on the calculated diagnostics. Now let's perform a diagnostic analysis that excludes prognosed failures. To exclude prognosed failures from a diagnostic analysis, the analyst simply marks the desired test sets on the Prognostic Options panel and then selects Exclude Prognosed Failures from Diagnostic Analysis as the algorithm. And when you calculate diagnostics, notice that the option to calculate prognostics is no longer available. Rather than build a prognostic sequence, you will be building a diagnostic sequence that excludes prognosed failures. And if we recalculate fault detection, the first thing that you'll notice is that the prognoses are removed from the flow diagram. And when we click on the final node in the diagram, we see that we're capable of detecting 50% of non-prognosed failures to this system. Likewise, when we generate the detection order report, no prognoses are listed in the detection order. This report also tells us that our total probability detected is 50% and breaks this down for each of the 2 tests. Finally, notice that the aggregate failure rate is now only 300, which is of course 60% of our total system failure rate of 500. The other 40% of the failure rate, of course, represents failures that we do not expect to occur, thanks to prognostics. This also can be seen in the mean time between failures, which has increased from 2,000 hours to 3,333.33 hours. This tells us that in this sample model we were able to extend the time between hard system failures by over 1,300 hours using prognostics. I mentioned earlier that the true value of prognostics has nothing to do with its impact upon diagnostics. The increased time between hard failures, the partial elimination of critical failures, the luxury of scheduling corrective maintenance at a time that is convenient. These are some of the benefits that are expected from the substantial investment both in money and time that prognostic development demands. But after all the money is spent, the sensors developed, and the laboratory experiments concluded, it must still be remembered that the horizon and accuracy predictions associated with newly developed prognostic measurements are often little more than elaborate swags. It is, if not impossible, then extremely difficult to come up with accurate predictions of how a system will behave under prognosis. And yet there's an entire industry pretending to do just that. I don't doubt that the condition-based sensing of impending failure is achievable in a great many areas of a system's design. Whether the actual performance of these sensors lives up to the hype and justifies the costs of development is another question altogether. Why do I mention this here in a video about fault detection? Because it is essential that the detection of critical failures, failures that can result in a loss of mission, equipment, or life, be fully realized within a system's diagnostic strategy. In other words, the existence of prognostics should not be used as an excuse to not develop diagnostics. We have just seen how Express can be used to calculate fault detection in a study that excludes prognosed failures. If the accuracy values for these prognoses are overly optimistic, or the true horizon is substantially shorter than that predicted, then the burden must fall on the diagnostics to identify when a failure has occurred, the malfunction causing that failure, and the appropriate remediation for the situation at hand. With this in mind, it would be wise for development contracts to continue to require a high level of diagnostic detection for critical failures, even though prognostics may be developed to try and prevent these failures from ever occurring. This concludes this video tutorial on the analysis of prognostics-informed fault detection in Express.